So we're going to have two videos here. Again, think of this integrative metabolism learning unit as being a meta-analysis, if you will, of everything that we've done in biochemistry. There's really not anything that's new. It's just pulling it all together, seeing that 30,000-foot view, and that's why these sort of concepts are a focus of the final exam. I know it's still a lot of information, but it's not the weeds that we talked about for each individual learning unit. So I'm going to walk through this slide right now. I'm going to do a lot of zooming in because right now we're at this 30,000-foot view. We'll dive in a little bit. And one of the things I want to highlight is when you see slides like this, you should be able to look at every single arrow that's there and tell me something about it. So for this in particular, I'm going to tell you the things that you do need to know. Okay, so zooming in here, again, first we're going to talk about the fact that we've got, if you think about from a nutrition standpoint, remember, I teach this class very much from sort of a nutrition, a health, and a disease standpoint. So when we think about what we have, oops, I did not mean to do that. I meant to do these guys. When we think about what we have in terms of what nutritionalists will call your macronutrients, that's what we have that I've highlighted in purple here. So these are your macronutrients, right? We've got carbohydrates. Now again, this says glycogen here, but we're just going to sort of highlight that we think about this as carbs, carbohydrates, we've got proteins, and then we've got lipids. If we think about macronutrients from a dietary standpoint, right, those lipids really are going to be triglycerides largely that are in our food products. Carbohydrates are going to be a variety of different options, but generally they're going to be glucose polymers. They're going to be glucose and fructose together as sucrose, right? So maybe we'll sort of even write these down. We've got starch that we can consume. We are going to have sucrose that we can consume. We can have fructose that we can consume, and maybe just we'll think about lactose that we can consume. Those are things that I want you to know, right? Starch is a polymer of glucose. Sucrose is glucose plus fructose. Fructose is a monomer by itself, and we'll talk about high fructose corn syrup, and then lactose is a polymer of galactose and glucose. So those are pieces that I want you to know. Again, but these are our macros, and then protein, right? That's the name that we have for that macro. So highlighting that our macros are going to be polymers, right? So macros are going to be polymers. So one of the things that I want to make sure that you know is what the linkages are that hook these polymers into, or make those polymers from their component monomers. All right, so we're going to talk about our monomers here. And I'm going to use this green color to highlight a lot of different monomers, which we're going to also refer to as our metabolites. So we're going to highlight a lot of these in green, but I'm just going to start here with what we might think about from a nutritional standpoint, sort of these building blocks that we have. So monomers that we have to build lipids are going to be fatty acids. And I'm going to highlight too that we need to have glycerol. We need to have that glycerol backbone, right? We've got fatty acids that are hooked on our glycerol backbone there. We're going to have glucose. If we think about it as the phosphorylated form, that first step of glycolysis, we've got glucose 6-phosphate, and then we've got amino acids. So we know that monomers interchange with their polymer forms by either forming or hydrolyzing those linkages. So let's go ahead and review what those linkages are. I'm going to start zooming in from time to time here because otherwise it's going to get really small. When we think about those fatty acids that are hooked on that glycerol backbone, what hooks my fingers to my knuckles is an ester linkage. So we've got an ester linkage that's going to hook those fatty acids to that glycerol backbone. Not really a polymer in the sense that we're hooking multiple together, but again, thinking about we have a linkage that we need to break in order to access the monomer form that we use biochemically. So we'll get to sort of some of these other words here in a minute, but want to remind you that hooking together all of these glucose residues, that is going to be a glycosidic bond. And I want to highlight that we have the importance, the distinction between an alpha and a beta glycosidic bond. When we have alpha glycosidic bonds, right, that is what we refer to as fuel. Beta was going to be fiber. That's sort of an important piece here. And that's the last linkage we want to talk about is when we hook amino acids together, we've got an amide linkage, or we also refer to this as a peptide bond. Right, so those are the linkages that we have. I'm going to zoom back out here for a second because I want to compartmentalize these macronutrients in two ways as well. Even though we have three things that sort of make up our dietary plate, if you will, and when you see sort of and talk about different diets, there's a protein component, a carbohydrate component, and then a lipid component. But these are not all sort of created equal. And I'm going to bin them in this way, and I think you guys will know why I'm doing this. But when we bin them in this way, right, and hopefully I'm not writing too much over our pieces here. When I have carbohydrates and lipids together, I have those together because these are the two main fuels that we have. When you consume carbohydrates and lipids, generally you are using them for energy. However, when you consume proteins, the purpose of protein consumption is not for energy, even though it's, again, worth 4 calories per gram. We'll probably put those numbers down here in a minute to remind ourselves of that. But these are building blocks. Let's see, we're going to have to give ourselves a little bit more space here. Building blocks. Right? We do not consume proteins intentionally for fuel. If they're in excess, they can be broken down for fuel. Let's put these numbers in here. Let's put our calorie values, right? We remember that proteins are worth 4 calories per gram. Carbohydrates, wow, I'm running out of room here. Maybe we'll put this over here because both of these are worth energy, but we've got carbohydrates, let's do this, is going to be 4 calories per gram. And then lipids are going to be 9 calories per gram. Right? Big difference between carbohydrates and triglycerides. We talked about this a lot. We've got a hydrophobic fuel and then a hydrophilic fuel. So we got a lot of transport issues that we talked about when we dealt with triglycerides versus carbohydrates. All right. So that was sort of our starting point here. And again, hopefully nothing new there. This all should be a review, but really seeing it in sort of this meta-analysis way. What I want to do here is I'm going to highlight, I'm just going to go through and highlight the important metabolites that we are going to see as I sort of talk about each of these arrows, but I want to highlight them first. You need to think about these as important branch point metabolites. So obviously G6P is an important branch point metabolite. Pyruvate, an important branch point metabolite. 3-carbon piece. You should be able to draw these. You should be able to draw me pyruvate. You should be able to draw acetyl-CoA. Not the CoA part, but remember what an acetyl group looks like. Draw oxaloacetate. Draw urea. Other metabolites that we're going to sort of map on here as we sort of see them is I'm going to talk about cholesterol. I'm going to draw it over here because it's sort of related to sort of the lipid piece. Citrate. Putting it over here because, again, it's related to the lipid piece. We'll see why when we sort of take a little bit of a deep dive here. And I think those are the important pieces that I want to talk about. But what I'll do right now is I'll just go through almost like, hey, we had one learning unit on this, and I'm going to sort of show you we're going to march through the entirety of the course here, highlighting the main pieces that you need to remember. Okay. I'm going to start with our first learning unit. We learned about glycolysis, right? That was the main learning unit that we had. Here's all that you need to remember for glycolysis. Glycolysis takes glucose, makes it into pyruvate. The rate controlling enzyme for that was PFK, okay? Other pieces that we're going to highlight here, and I'm just going to sort of show it here. I want you to think about cellular location. When we learned about, and we're going to call this cyto and mito. Glycolysis occurs in the cytosol, and then everything else that we learned sort of from a carbohydrate metabolism standpoint happened after that, okay? So glycolysis occurs in the cytosol, and then we get to pyruvate, okay? Pyruvate basically needs to go into the mitochondrion, and that's why we are going to have then pyruvate dehydrogenase chemistry. happening in the mitochondria. All that E1, E2, E3, all of that stuff that you don't need to know that at this point. I need you to know that pyruvate is converted to acetyl-CoA by pyruvate dehydrogenase. Okay. Then we've got acetyl-CoA. We really didn't talk about the control of the citric acid cycle, so no enzymes that you need to remember from that, other than, I'm going to map on here, look at this, when we need to take oxaloacetate and take it back into pyruvate, that requires us to then think about utilizing the malate aspartate shuttle. Okay, I don't need you to remember all the details for the malate aspartate shuttle, but when we need to get things like oxaloacetate back out into the cytosol, we don't have a transporter for oxaloacetate, but we can convert it into malate, which we do have a transporter for. So that malate aspartate shuttle is really important. So that essentially then took us on to oxidative phosphorylation, and that was like the first half of the course, sort of learning those pieces. We then sort of talked about fat metabolism. So I'm going to kind of dip over here for a second, highlighting that here's the pieces that you need to know. Rate controlling steps, right? Rate controlling enzyme for fatty acid synthesis was ACC. We didn't have an enzyme that we learned about for beta oxidation, but we learned that the rate controlling step for beta oxidation is that influx of fatty acyl-CoA into the mitochondria. Right? And that was that carnitine transporter. Okay? So already sort of said it here, so let's highlight that beta oxidation occurs in the mitochondrion. Fatty acid synthesis occurs in the cytosol. Okay? Some other things related to fat metabolism, right? That beta oxidation piece generates acetyl-CoA. Now, when we have excess acetyl-CoA can come from any fuel. We're going to see that when we finish sort of our protein arm over here. But when we've got acetyl-CoA that we want to make back into fatty acids, again, that's fatty acid synthesis, right? We are going to export that acetyl-CoA. There's no transporters for acetyl-CoA. These are some of these pieces to sort of know about. No transporters for acetyl-CoA. So we export acetyl-CoA via citrate out into the cytosol so that we can then do fatty acid synthesis. Another thing that's related to acetyl-CoA is ketone bodies. So we zip together acetyl-CoA molecules. 2 + 2 is 4. Another 2 makes HMG-CoA. So HMG-CoA, I shouldn't put this in red. This is really a metabolite. Let's do this. Let's put this in not red. Let's put this in green here because we've got HMG-CoA. So HMG-CoA is a 6-carbon piece that's put together from 3 acetyl-CoAs. And then that is a precursor that can be used to both synthesize cholesterol and then make our ketone bodies, right? So I want you to remember HMG-CoA. So HMG-CoA is a common precursor used to both synthesize cholesterol as well as ketone bodies. Let's see here, just looking at my notes, seeing other things that I want. I don't think there's anything else I want to say here about carbohydrates and lipids, right? So that got us through to our 7th learning unit. And then we went and we did amino acid metabolism, protein metabolism. So let's sort of come over here. I do want you to remember and think about when you've got proteins that are broken down into amino acids, we have a fundamental elemental problem there, right? We've got nitrogen. That is an element, an atom that was not present in any of our fuel macronutrients. So we need to think about how we deal with that, right? So when we've got amino acids, we basically are going to do amino acid degradation, and we are going to collect all of the amines, all of those nitrogen atoms as aspartate and glutamate, right? So we're going to have transaminase chemistry. That transaminase chemistry is going to allow us to collect things as aspartic acid. So here's another metabolite, and glutamic acid, right? And I'm going to highlight. I should be highlighting here in green any of our important metabolites. So go back there, HMG-CoA. We've got glutamic acid and aspartic acid. Actually, I'm going to zip and put glutamic acid over here. Hopefully you'll see why. Glutamic acid, right, is the alpha keto acid. Oops, I didn't mean to put a glutamic acid over there. Glutamic acid, come back over here. Aspartic acid, oh, come on. Aspartic acid is the alpha keto acid skeleton of oxaloacetate, right? That's something I want you to know. But we build urea from glutamic acid, aspartic acid, and oh, you should know this guy. We've seen this quite a bit. Another sort of metabolite, if you will, bicarbonate, right? And a super important enzyme that we've learned about. Let's see. We can take carbon dioxide, and I'm going to sort of put these maybe as in green as well. Carbon dioxide and water, sort of important metabolites, if you will. And then we are going to use carbonic anhydrase as a way to synthesize the bicarbonate that we need. Move this over just a little bit, right? And that's how we build urea. We build urea from aspartic acid, glutamic acid, and bicarbonate. That's how we build urea. All right, I promise just a couple more things that I want to have on this. I know this is a really overwhelming slide, and when we zoom back out, there's going to be a lot there. But again, building it a little bit at a time is hopefully something that sort of puts these pieces together for you. Let's see. So again, we've got glutamate there. I think the last couple of things that I want to add are, notice here with amino acids. Amino acids can be converted into pyruvate, or they can be converted into acetyl-CoA. So when we have amino acids who are deaminated, right, by transaminase chemistry, and we have that alpha keto acid skeleton be able to be converted into pyruvate, basically we call those glucogenic amino acids. So glucogenic amino acids, right? So from a metabolite standpoint, we've got glucogenic amino acids, and then we also have ketogenic amino acids. Those are the ones that can be converted into acetyl-CoA, okay? And so one of the other sort of relationships that we learned about is the amino acid alanine. So again, alanine is the alpha keto acid skeleton of pyruvate. Aspartic acid is the alpha keto acid skeleton of oxaloacetate. I think there's only one other little thing that I want to map on here, and that is highlighting the importance of, this is one of the only one-way arrows that we see there, and this is super, super key for what we see here in terms of our cellular biochemistry. We cannot take acetyl-CoA and make it into pyruvate, which means fats that can only be made into acetyl-CoA cannot be made into pyruvate, which means they cannot be made into glucose. But if you have, and I'm going to sort of put over here, same color here, if you have a glyoxysome, if you have that particular organelle, you actually can do that chemistry. You not as a human, you as an organism, right? And we talked about different organisms, seeds from plants that have glyoxysomes so that they are able to convert fats, storage of energy in seeds, into carbohydrates so that they can grow plant material. Super cool stuff there. All right. Wow, that was a lot. I think that's all that I want to say on that slide. Oh, just want to highlight anything that I've highlighted in red here. Those are going to be enzymes that you should know. All right, so anything in red there are going to be enzymes, and then anything that we had there in blue, not a lot, but just a couple of times we referred to location. So thinking about cyto versus mito. So cyto versus mito. I think that's all that I want to say. I know that's a lot, but wow, 30,000 foot view, nothing new, just sort of trimming it down to the bare bones of things that I want you to know for this last learning unit.